So let us begin with the watershed concept first. So watershed is the area that is drained to the common outlet. This common outlet can be your reservoir, your rivers, or even the ocean also. So watershed is the basic building blocks. That means it is a basic way of doing the land and water planning and management. So when you talk about land and water, it's just not a land and water, it's a vegetation also. So biomass also generated with the help of land and water. So it is a combination, it's a three-way approach, like land, water, and biomass. In another definition, it says that area that supplies water by the surface or subsurface flow given to the drainage systems of a body or stream or river. So common outlet can be a stream, river, wetland, lake, or ocean. So anything. The third definition is watershed is a geohydrological unit comprising land and water within the confined drainage divide. So this is a definition that is adopted by FAO, Food and Agriculture Organization of United Nations, in 2001. So this is how it is defined. Now it is very easy to read that line, but when we see how the watershed look like, the watershed, it should ideally look like this, where if you see the red line here, just let me, oh, sorry. If you see the red line here is the defined boundary. This is a ridge line. So I will talk about what is the ridge line. There, just remember, this is the boundary of a watershed where the water from these goes into the streams, and then streams form the rivers, and then goes to the ocean or water bodies. So area that is covered with the ridge line and draining to the common outlet is the watersheds. Now there are various terminology that used in the watersheds. So let's learn about those terminology. The first is the headwater. Headwater is the first place or the first starting point of a stream where the water starts coming in. And how the water will start coming? With the help of precipitation, that is a rainfall. So rainfall or the precipitation is an input to start the runoff or start the water flowing from the rivers or surface of the soil or land and drain to the small streams and then become a river. So ridge line is nothing but the highest point which divides the two drainage line. Now you can see, if this is a pink line, the water of this area will drain this side and water on this side will drain to this side. So it is a highest point where the water directions divide, and joining these ridge points become the ridge lines. Some of these tributaries you can see, and then when you go to the downstream, then floodplain starts. A floodplain is a low-lying area where water starts accumulated. So you must have been seeing in your Satara or Kolhapur, where the Krishna is being turned into many other zigzag way and become a floodplain in many times. And then estuary is near the sea area. So these are the basic terminology where you will learn the watershed concept. So let's talk about few more watershed concept. This is one ridge line, yellow one, and this yellow ridge line, it's a dividing of main drainage line, that is basin line, and this is a river where the common outlet goes. Now within the watershed, you may have various small streams that can be your sub watershed also. So this is one watershed of these streams draining into the one single point. Then at this stream could be a one sub watershed, these streams could be one watershed, and this could be one watershed. So likewise, within the watershed, you could have many sub watersheds. Now, if you plot the contour line, so contour line is nothing but the point joining the same elevation. So these are the imaginary line. Contour lines are the imaginary lines where the elevation of equal where the points of equal elevations joins together to form the elevations. If you see here, the elevation, it goes like this. So uphill like this, it becomes streams. And when the contours forms or change the level, then it becomes your ridge line, like in the case of this. Yeah, this is the one other example where you can demarcate your watershed boundary using the contour or using the drainage. So these black lines are the contour lines where the elevation is written on it, and the drainage. And watershed boundaries are based on always it is based on the topography. Unlike our administrative boundaries like taluka, districts, or state boundaries, these are the administrative boundaries. They don't behave according to the topography, but the watershed boundary always follow the topography. Topography means the elevation or a land surface elevation of particular area of interest. Now, if you know how you can delineate the watershed, so before that you must know what are the different concepts in the topo sheets. These Survey of India topo sheets, they give many important features wherein you can delineate those watershed. But before that, you must understand what are these things that is available in a Survey of India topo sheets. So these topo sheets are available free of cost now. From the Survey of India topo sheets. You can yourself download it and then study it. This contour interval is the vertical distance between the two contours and generally never cross each other. These contours always goes parallel to each other. They never cross each other. They can be close, but they never cross each other. So always remember. And here you can see one contour with a name or label that is called the index contour. This index contour is written on the topo sheets or Survey of India maps because it gives a elevation value of that particular point or particular line. And these are helpful to see how the topography is behaving from the ridge to valley. The third important, hilltops. These hilltops becomes on the top of the hill where the surface is nearly a flat, like a plateau. You can say plateau, but these are the hilltops are generally have a very close contours on smaller size or the smaller size contours. Then contours close together indicate a steep slopes. Now, if you see here, the contours are very close to each other. So interval between two contours are very less. When you see the dense contour, that time you can assume it that area is very steepy slope, means steep slopes. So contour close to each other is always indication of steep slopes, and contours far away from each other is a gentle slope, like here. You see here contours are separated much wider than this area. So these are the floodplain or kind of a gentle slope lands. And the green color is a forest cover in the topo sheets. So another example of this, the spot elevation. The spot elevation in the topo sheets are with the known elevations. So these are nothing but the points where the elevations are recorded at that particular points. And when contour line cross the stream, they form the V shape. Now, if you see here, it forms the V shape that always point up hills. That means this is kind of a uphills towards uphill. This is a hill, and then it starts draining this side. So if you see here, it starts with the V. V means towards the drainage line, not on the upstream side. The next terminology is saddle. This saddle you can see here is a lower area and on the higher elevations like a flat. So these are the flat region on the top of hills or on the higher elevations areas. Depressions are indicated with the close line. Now you see here the depressions where the floodplains occurs. These are pointing inwards and inward pointing ticks. Like you can see here, may not be able to see, but these are the closed polygons are the closed line contours. Those are the depressions. Then one of the important thing in the topo sheet is the benchmark. This is called the benchmark. This benchmark is a known point of elevation and position. Yesterday we talked about latitude and longitude and elevations. So these benchmark points on the topo sheets use the value of x, y, and z. Z is the elevation. So x is your x is your longitude and y is your latitude. And those gives the x and y points on which you can then start your survey. You can take this benchmark for your area of interest from the topo sheets and start doing your survey using the total sessions or using the DGPS and any other methods. So these are the few of the important nomenclatures that is available in topo sheets and their meaning that will help us to understand how watershed can be delineated using topo sheets or using DM. The second important concept of watershed is a stream ordering. The stream ordering is considered as a fundamental exercise because it starts with the order number 1, 2, 3, and 4. And there were two methods, the Horton methods that is originally developed to develop a stream orders, and then Streller method. This methods is been modified the Horton methods and gives a more practical and application oriented. So we learn about those waters stream ordering. Now you can see here the single order stream is nothing but there is no other streams are joining to this and then become a stream 1. The stream order, the highest order is this is the lowest order. This is the lowest order is 1 stream, and the highest it can go up to 12, 13, 14, depending on our watershed size. And then when 1 and 1 joins at one place, then it becomes a stream order number 2. When stream order of 2 and 2 joins, then it becomes forms 3. It might possible that the stream order may join by 1. Then also it will be 3 because the higher order it takes. Because higher order. So 3 for this three number order streams, 1 is also joining. The number will be remain 3. And when 3 and 3 joins, then it becomes 4. And here also a 2 number of orders can also be joined here. But in that case, then it will be a 1, 2, and become 4 because already 3 is here. So likewise, this hierarchy of stream orders are maintained, and this is a very important in the watershed analysis or watershed delineations things. The stream ordering. The first order is always a single streams, and it does not have any tributaries. Now, how you can delineate the watershed using the topo sheets? It is just an example here. First, you identify the watershed outlets using the help of a stream or joining 2 streams together. Now here, the 2 streams are joined together. Here it is marked as a circle point is a common outlet. Then what you can do? Look for the ridge line and saddle. The ridge line is the one where it divides the 2 drainage line. Now you can see here, these are the drainage line. These are the drainage and these are the ridge line, cross one, because the stream on the right side will go flow in this way, and the left side the stream will go in this way. So water will flow here and there. So this is a ridge line. So you can see the contour here 200, and then go up, and then you can find here a saddle is here, and one saddle is also here, and then again a ridge line, and again a ridge line, and then again is floodplains. Likewise, you can cross all those points, and then you can form the closed line. You can join all those points together to form a ridge line of a watershed boundary. So this watershed boundary is nothing but a point joining a ridge points and saddle points. So this is how you can, with the help of topo sheet, you can delineate those watersheds. Now, these watershed delineations are automatically done with the help of many GIS and remote sensing software, using the help of your elevation data, that is digital elevation model. So digital elevation model, or if you have a contour of a particular area or elevation survey of a particular area, using the elevation point, you can generate the contours, and from the contour generations, you can delineate these watershed for any common outlets or any point. So this is how you can delineate those watershed also. Okay. And then next is what are the different watershed parameters and the geomorphological parameters. That means a geological and total physical structure of watersheds. It depends on many things actually. First is a climate, which governs the temperature, precipitations, moistures. Then size, it can be a micro watershed, sub watershed, basin, catchment, or sub basin, and so on. And the shape, how it looks, and then drainage, the drainage ordering, drainage pattern, then frequency, stream ordering, stream length, and the density of the watersheds, hierarchy, the ordering of watersheds. As I told you, the watershed, there could be a sub watershed within the watersheds. So ordering of those watershed also important. Then geology, how the soil and rock are forms in the watersheds. Slope and aspect, how the gradient and the aspect ratio is there, means the direction of the flow as well as the direction of slope. Soil, the soil textures and type. These also very important characteristics in the watershed terminology. The hydrology, how the water behave and responds with the various climates, land use, and then management practices, cultural practices, and so on. Land use and land cover, that is how it is available. And then socio-economic, that the people that is living in the watersheds also influence the watershed characteristics. So these are the few parameters where the watersheds are being influenced by their characteristics. We'll look into the few of those parameters in detail, like a length of the watersheds. This length of the watershed is generally measured from the path where the greatest volume of water would gradually flow. So that means if you say that in this the water starts from here, and then in the next order it goes like this. So this could be the length of watershed, because the water flows with the greater volume in the second order, third order, fourth order, and fifth order streams, and this can be your length of the watersheds. And there are different shapes of the watershed. Now you can see this is a elongated, like a caterpillar shape, and then you can have a circular shape, a fan kind shape, then pear type shapes. This is an irregular shape, then tree type shapes. This is a fan shape, like your fan blades, a table fan blades, like, and then fern or leaf shape watersheds. These are some of the shapes of the watershed, but it not necessarily it should be exactly like that. But normally, if you see any watershed, it should be look like something like this in the watersheds. However, it can be in very high undulating areas or in the hilly areas. these watersheds can be of irregular shapes. So there is no defined shape of the watersheds. It's just an indication of how the watersheds are formed in a basin or in the catchments. Now there are different sizes of the watershed also. And according to the Watershed Atlas that is published by the Soil and Land Survey of India, these are defined in different ways. Now, if you see here on the number 1 category, the water resource region, the WRR, there are some water resource region like you have western regions, you have eastern region, then you have Himalayan region, and then you have a desert region. So these regions are defined and their size is much bigger. Its average size is more than 5.5 crore 5.5 crore hectare. Then next comes the basin. Our basin is like your Krishna basin, Godavari basins, or your Kaveri, Narmada, and Ganga, and all those things. These are the basins because this covers a large, really large area of 95,000 hectares, 95 lakh hectares. Then catchments are more smaller than the basins of 30,000, like your Wine Ganga, Pen Ganga, or you can have a tributaries of your Mula Mutha. These can be the catchments for the Krishna basin also. Then you can have a sub catchments. Within that, there could be some small streams. Those can be of order 7 lakh hectares area. Then watersheds. Normally the size of the watershed is 80,000 hectare area. Then sub watershed is around 7,000 hectare area. Then micro watershed is average size of 700 hectare area. So the smallest unit as per the Watershed Atlas of India and from the Soil and Land Survey of India is the micro watersheds of 700. So, and normally the planning is planning of any land and water management are done with the help of micro watersheds. And when it goes up in the basin or the catchment, then it is called the river basin plans. So watershed plan or micro watershed plans or some land and water management plans are generally governed in this area, and then it goes up to the basins. So micro watershed planning is happen here, and then river basin plans are happens at this level. The basic principles are remain same while planning and management. The things will be differ when you go to the basin level. That's only. And sometimes this catchment is also synonymously used with the watershed as well. There are some formulas for the defining the morphological characteristics of the watersheds. You can just think of those morphological parameter like a stream order, the hierarchy or rank 1 from 1 to so on, the stream length of the streams, the main stream length, where you can have a total stream length of order divided by total number of streams of segment order U. So how many streams order of particular order are there divided by total number of stream segments. Then you can have a bifurcation ratio. Bifurcations means number of streams order of n plus 1. So how the ratio, your streams are bifurcated from each other. Drainage density, which is very important, which gives a density of drainage in the watersheds. That is the total length of the stream divided by the area. And the reference, you can see these are the references for those morphological characteristics. Then another, the stream frequencies, where stream frequency is the total number of streams of all orders divided by total area of the basin. You can see here. And then drainage textures, where the total number of streams of all order and divided by perimeter. Now, these has some different meanings in the watersheds. When you do actual calculation on those, then you will have a very different numbers, and those numbers define the characteristics of watersheds. It is a form factor, which is another important characteristics of the watershed. it is called the A divided by LB, that is the area of the basin, and the square of basin length. So what is the basin length? Basin length is the length of your ridge line, and then that means you can say it is a perimeter of your basin. Then circularity ratio, the area of the basin divided by square of, sorry, this is the length and this is a square of perimeters. So that gives the circularity of ratios. Then elongation ratio, it is divided by area of basin by the basin length. So this is the basin length, that is the length of the basin, maximum length of the basins from your outlet to the topmost point. Now we look about the different components of the watersheds. Basically, there are, as I told you, there are basically three watershed components. The first is land management, second is water management, and third is biomass management. These three basically and mainly, these are the three components. And under these land management, then we can have a different slope characteristics like a slope, formation, terrain, depth, moisture, texture, soil capability, infiltration ratio, geohydrological formations, groundwater capacity, and all those things. How the ground are there. I mean the what do you consider that? When you dig the soil surface, and then you will have a strata. So ground strata, how it defines. Those also can be the land management. These land managements are very important when you have to define with many water conservation structures and some soil conservation structures as well as water conservation structures. Then next comes the water management, where the management of different water components. So water component like inflow, like your rainfall, groundwater or surface flow, then outflows, groundwater flows, subsurface flow, and water flows, and then water uses. Some drinking water. Water uses means the water is consumed by the various users. Like drinking water we use for our domestic purpose, then irrigation by agriculture, and evaporation and evapotranspirations. Those are things. So these are the few of the things that governs. So I think most of the people know about those terminology. Then storage, then it can be stored in the root zones. It can be stored in the surface storage like your depressions or lakes or ponds. Then some are water is stored as a groundwater components. So in the third component, last is biomass management. So once you have land and water management, naturally you can expect some biomass or some vegetations. And those vegetation management are the biomass regenerations. How the biomass is generated every year and now after the rainfall periods or after the rainy seasons. These biomass management also can be in the help of ecological preservations. Now it is mandatory as per that any watershed or any basin should have at least 33% of green cover. So, and most of the basins are not having that adequate amount of green vegetations in the watersheds. So 33% means a total 100% area. The 33% area should be under green cover. So green cover is defined as a permanent vegetations, including your horticulture as well as your orchards and or planted vegetations which reduce the soil erosion as well as increase the moisture contents and reduce the temperature. So this is the definition of green cover. And those green covers are now become a very important aspect due to this climate change impact on the various hydrological and water balance cycles. And then forest management and conservations. These comes under the biomass management. We'll look into the detail of those land management, water management, and biomass. Under land management, then we can define or categorize as some can be a structural measures. These structural measures are like your soil conservation as well as water conservation measures. So these soil and water conservation measures can be a contour bunds, earthen bunds, stone bunds, compartmental bunds, graded bunds, contour trenches, contour terrace wall, bench terracing, broad base terrace, and field bunds and channel, and then centimeter terraces. So there are based on the slopes. Based on the slopes, different type of structures are required in the watersheds, and therefore the contours, the elevation, the topography plays a very important role. Rather, it is the only one which drives all your land management practices in the watersheds. The second is the vegetative measures, how the vegetation of the plant, their growth and mulching, vegetative cover, grassland, agroforestry, and whatever fencing and more. These vegetation measures are important to reduce the soil erosion. So now we see there is a large amount of soil have been eroded, and many watersheds are under degraded categories, just because the vegetation, the loss of vegetations expose the soil, topsoil, fertile soil to the soil erosion due to the rainfall, due to the intense precipitations, or due to the you call it as a various kind of a soil erosion like a sheet, wheel, and gully erosions. So these different type of erosions happens due to the less plant cover or vegetations on the soil, which reduce the strength of the soil to hold at that particular point, and therefore the vegetations measures are very important to protect the soil, to reduce the soil erosion and protect the loss of topsoil. The third is the production measures. This production measure is agriculture practices, how you do the mixed cropping, cover cropping, strip cropping, crop rotations, and then contour cultivations, and how you prevent, or sometimes agroforestry and horticultures. This prevents the water to flow down into the flow out of the watersheds as well as soil. So these different kind of production practices or cultural practices help to reduce the soil erosion and conserve more water. These could be a good example for the agriculture. Now you can see here a different structural measure, vegetative measure, and production measures are required at different places. These are not at the same place. Based on the topography, based on the soil cover, and based on your land use, land cover, these are prioritized. These are prioritized based on your slope, based on the vegetations, based on the land cover, based on the land capability classification or soil, and based on your various land use, land cover practices. The fourth is the protection measures. These are mostly for the hilly or slopy lands where the landslide or very high intense runoff occurs, or like your waterfall. Like your waterfall or landslide, when you need to control the flood, immediate flood, which can have a devastating impact on the watershed downstream. So these are mostly governed in the very hill regions or where the slopes are very high. Where then you can give a landslide protection, some kind of a runoff flood control structures, or you can do some gully plugging and restrict the flow, restrict the velocity of flow in the stream. So this is mainly to reduce the soil, reduce the velocity of water flowing into the stream downside, and protect the land as well as vegetations. Now, as I told you, these has a different criteria on which these can be built. I'm just giving you one example how these conservation structures required how the conservation structures requires a different category of soil, land use, drainage, and then slope category. Just one example, this if you want to construct a check dam, then it should be nearly level to gentle slopes, maybe near to the river streams or near agricultural lands. So that could be the best. And then soil type should be a fine loamy and drainage up to third order only. It cannot go up to more than 3. So up to third order, these check dams can be constructed. And the catchment area, catchment area is a watershed area. So as I told you, watershed and catchments are synonymously term each other. So catchment area is the watershed area up to 25 hectare. You can have these check dams in the rivers or streams. Then percolation tanks. This percolation tank, this percolation is nearly level to very gentle slopes. And these are mostly on the open land or wasteland because it occupies large area for storing of water, and then mostly clay loam. Clay or black soil is very fine for this percolation tank because the black soil or the clay soil has very, very less infiltration rate. So water going down below the soil or below the subsurface is very less, and then you can retain the water for maximum period of time. These can be on the second order or third order and should be of 5 hectares. Should be of 5 hectares or greater than 5 hectares. Nala bunds, these should be on the nearly level to very steeps and the open land and the wastelands, and then you can have a loamy, that is the best. And up to this nala bund is used for recharging groundwater, and therefore you could have a loam or sandy soil where the water can penetrate into the groundwater. So different structures will have a different purposes and according to their constructions. Now slope category. Used for design, style, and water conservation structures. Just to mention this slope category, these are the categories. Nearly level means what? A 0 to 1% is, these are the tentative, these are not fixed. That nearly level means 0 to 1% slope. Then very gentle sloping 1 to 3, and so on. Extremely steepy is greater than 50% slope. So these are the different category of slopes used for designing and construction of different soil and water conservation structures in the watersheds. So remember, in this case, the topography, the elevation of the watershed plays a very important role, and therefore this the elevation survey or topographic survey are being done with the help of dumpy level, with the help of your total stations, with the help of DGPS, and generate the contours to demarcate various features like a steep, ridge line, strip line, and river line, and so on. And the next is components water management. This is more important than your land, because land, we have abundant land, but the water we have very scarce water, as well as for limited period. It is not available throughout the year. So for only 4 to 5 months you get the rainfall, and then rest of all the months you have to manage it. So water management is the one which is the most priority in many watershed today. And this you can categorize into different components or different category, like inflows. These inflows could be your groundwater inflow, that you pump the groundwater and put it to the surface, or some precipitation or rainfall, and then surface water inflow. It can be a surface water inflow from tank or pond. Then outflows, groundwater outflows, surface water flow, or runoff draining to the streams, rivers, nalas, and as well as to the water bodies. Then water uses. These water uses can be a drinking water, irrigations, water, then evaporation, evapotranspiration, and one more you can add is here's industrial water use also. Now this industrial water use also is becoming important things for due to the enhance or rather improving the economic structure of the watersheds. So more and more industries, more and more service industries are coming up in the watersheds, which use more water for their daily needs and consuming more water. So those water user can industrial water use can also be clubbed into the water uses. Then once you water, then it store the water. It can store into the root zone. It can store as a surface storage like water bodies, lake and ponds, and the groundwater storage. Now here important thing is that groundwater storage is abundant. Groundwater storage area is abundant, but the groundwater is limited. So we have very large amount of groundwater storage. Naturally the God or the nature has given us a empty of space under the ground. You can store the water, but we are not storing the water. We are just pumping it, and therefore this today in the today's many of the government program, you might be knowing the Atal Bhujal Yojana. That is Atal Bhujna that is running around 7 states now today. In the Maharashtra, in the Gujarat, in the Karnataka, Rajasthan, and Madhya Pradesh. They are going for the massive recharging of groundwater for 10 years. So last year, this project was started with the help of World Bank under the Ministry of Agriculture, Ministry of Jal Shakti, and this is a massive project of 10 years where they are replenishing the groundwater. And bringing groundwater level up to the previous 3 decades ago, like into 1980s or 1970s, when what was the groundwater level, that level they are trying to bring it, because that is the possibility where the storage can be possible. All the surface storage, most of the surface storage in the basins are now exhausted. There are no surface storage possibilities. As of today, the only possibility is storage in the groundwater only. The fifth one, that is the quality. Now, these are also coming into the picture, and very important is the surface water quality as well as groundwater quality. These are some 5 aspects of the groundwater management, water management. Then we'll learn about some few terminology of those things, how the water management in the watersheds happen physically in the watershed when the precipitation or the rainfall starts occurring here. So precipitation and rainfall is same. That is the amount of water falls in particular area. Amount of water that falls in the particular area, that is the watersheds. Then you can either have from the precipitations, you can either have a infiltration to the soil if that is open to the if it is a bare soil. But if there is a plant, then you can say the water falls in the plant leaves, and then plant also stores some water, and that is called the interception losses. This interception losses happens if there is a tree or if there is a vegetations. And there is one important thing is here, interception losses are directly proportional to your leaf area index. So leaf area index is nothing but the amount of the area of leaf area divided by total area of canopy area of a tree. So this is how the interception losses are also coming into the pictures if there are large number of tree or many trees. So these interception losses, and then finally this interception losses goes into again soil, and this from the soil it can directly infiltrate into the subsoil, and some portions may go as your overland flow that flows on the soil surface. And when the soil surface, the water flows from the soil surface, the depression gets stored. if there are some depression areas or the like low-lying areas, then it get filled first and then it starts flowing down. When it comes to the groundwater, the water that flows from the subsoil through the infiltrations, it then percolate down to the groundwater tables. This is a groundwater table where the groundwater are stored. And once it is infiltration is done, then percolation starts. So infiltration is always from the downstream side, from the subsurface soils, where the percolation is always from any directions. Percolation of water, these two terms are different. Percolation and infiltration are two terms are different. So you should remember that percolation is in any direction. It can go into 360 directions. However, the infiltration is always from the top to bottom. It will never go as a horizontal movement of water. So horizontal movement of water is termed as a percolation. Then it contributes to the groundwater flow, and then groundwater flow also flows according to topography and goes to the streams and rivers. Then it flows, it goes to the river, some river or stream. When the groundwater flow to the stream, then that is known as a base flow. You can see here. A base flow. So the base flow is when the groundwater table flows to the stream and becomes a surface water. Then it is called the base flow. And it takes more than 1 month or 2 months to contribute from the groundwater table to the streams. That is reason if that groundwater table goes down and down, your streams also get dried up frequently because there is no groundwater base flow to the streams. And that is the main reason that most of the rivers and the streams are getting dried, because there is no movement of water after the rainy seasons. Then you can have this once the water flow starts from the surface, then that is called the overland flow. This is the base flow and this is the overland flow. And this is sometimes also called the runoff. This overland flow also can be sometimes called as a runoff. So this direct runoff can be club of two things. One is overland flow and some are the interflow. Interflow means if there is some flow that is moving from the root zones. The movement from the root zones, that is also contribute as a runoff to the on the soil surfaces. And then some water gets stored in the soil as a soil moisture. So these are the some soil moisture. This is overall picture of how the water behaves once it is fall in the watersheds. And now once you got the idea of what happens when the rainfall comes with the with various land use and topography structures, then it is easy to plan your structures for the water as well as soil conservation structures. This water balance is the important and significant step in the watershed management, and this is precisely done in every watershed. They measure first is the rainfall, how much is the rainfall, total average rainfall of the watershed, and then losses, and then goes to the runoff. So mostly the watershed management concern about the rainfall and how much is the runoff. And runoff divided by rainfall is called the runoff coefficient. So this runoff coefficient of a watershed is important characteristics for the water management. So how much is the runoff and how much is the rainfall? The ratio of runoff by rainfall is the runoff coefficients after deducting the losses from the rainfall. Now, now the losses could be a number of losses can be there. Some interception losses that from the vegetations held by the different plant leaves, and therefore the effective rain that received by the soil is rainfall minus interception losses. So this is the basic equations of how effective rain can be calculated rainfall minus interception losses. Now, next goes the evaporations. So evaporation from the water surfaces like reservoir, lakes, ponds, rivers, and channels, and from soil surface, appreciably when the groundwater table is very near to the soil surface. Now, from the soil also, the evaporation starts. If there is no plant or no tree or no vegetation, then it will start evaporating from the soil. So it is a bare soil surface evaporations, and then surface water evaporations. Now, there could be a evaporation from the plant surface also. If there is a plant and water that is held by the various plant leaves, and then evaporation from that also, it can be contributed as a evaporation losses. But that evaporation losses is very minute or minuscule. So that can be neglected in calculation of water balance. Then third is a transpiration. This transpiration is the water that is consumed by the plant for its photosynthesis and released into the atmosphere. And that is known as a transpirations. So water leaving from the plant or streams or plant leaves is known as a transpirations. Then evapotranspiration, the fourth component is evapotranspiration for consumptive use. And now this is evapotranspiration is mostly from your irrigated or cropland, because evapotranspiration happens when evaporation from the soil or evaporation from the vegetations plus transpiration from the crop leaves to maintain its photosynthesis activity. So both combined together becomes the evapotranspirations. And this is mostly from irrigated and cropland. Then infiltration. Infiltration is into the soil at a ground surface, and then watershed leakage. This watershed leakage is the groundwater movement from one basin to another into the sea. Now, this is a watershed hierarchy. So you may have a subwatershed, subwatershed, subwatershed. So one watershed leakage could be the input for the another subwatershed downside. So this is how the water balance calculation for the watershed is done under the water management components. Now, another example of the water balance equations here, combining all these two together, you can then form as a simple equation of a precipitations plus subsurface flow, that is a input. This is called the input. And this input should be equal to the evaporation from water loss as a evaporation from the soil surface as well as from the water surface. Then evapotranspirations from the crops or vegetations. Then a subsurface outflow. Surface vessel out means percolations that go downhill. Then soil moisture that increase in soil moisture, that one, plus increasing surface runoff and groundwater recharge, because the groundwater movement is the one, and then groundwater recharge balance goes to the recharge to the groundwater. This is a broad equation for the for estimating the water balance of a watersheds, and then there are various methods and various thumb rules and various equations are available to calculate each of the parameter under this equation, water balance equations. Then third was the biomass management. This biomass management is to meet your need of food, fuel, and fodder. Now, when we live in the watershed, we always need a food to eat, and the animals needs a fodder, and the fuel needs for your cooking and domestic purposes, or making your water hot, and other for energy or for industry purpose, and so on. So that biomass generations, and sometimes you need a biomass management for preservation to maintain the green cover also. Then forest management, area protection, wildlife protection, sanctuaries, if there are anything that can be also maintain here. Eco-preservation also can be your recreation sites like your water bodies, to maintain your water bodies, to maintain the hygiene of that water bodies or the lakes or ponds, and then beautify that spot with the help of these eco-preservation measures. Then plant protection, social forestry. These are, because this is particularly for the people and therefore to maintain the biodiversity and engage people in the forest programs. This is particularly important because they have some role to play and their uses also. So they take some fodder, they set them some wood for building their houses or for their energy needs and so on. So therefore, this forest in the most of the forestry, the peoples, nearby peoples or local peoples are engaged to protect the forest covers and forest land also. So this is just an example of the biomass management. And the biomass balance also, you need to maintain it. And this biomass balance can be estimated with the help of your how much the food you required per year, and how much fuel you required, how much fodder you required for the your animal need and cattle needs for the entire village or for the community that is living in the watersheds. And then you can then define how much is the need and how much is the availability with the help of this biomass calculations. So you can calculate the biomass need and how much water is, how much biomass is available in the basin. So biomass availability is also can be calculated with the help of many formulas, and many rules are there in the various forest management courses and various forest or even biomass estimations books. These can be helpful to estimate this availability as well as need. So this is all about from my side on the watershed concept, various concept, various components, and how you can delineate the watershed and so on. For this lecture, I hope you might have understood many things. If not, then you can ask me questions, maybe for 1 or 2 minutes. So how subsurface inflow is calculated? There was one question, how subsurface. So there are various ways. Okay, there are various ways to calculate the subsurface inflow. The first thing is that the groundwater levels. So if you have some open water levels, open wells, or you have a tube wells with the groundwater level measurements equipment in that, then you can measure the water level in that every day, morning and evening, and then you can have a pumping test also. Once you do the pumping, and then how much time it required to recuperate at the same level. So if you expect a recharge quickly, then you can say that there is a water movement and then recharge is faster. The second way is if you have a stream and after post monsoon season, you can go into the that stream and measure the surface flow. Then you can measure the surface flow at the upstream side and then downstream side. So upstream side flow is actually your the stream flow, and then subsurface flow when it comes to the groundwater, then it also accumulated. So it's a little tricky to measure. In 2-3 ways you can estimate those two things together, but most precisely it should be from the pumping test, or secondly it is from the various water level measurements over a period of 2-3 months after the post monsoon. after the post monsoon. Okay, you can. Is there
Anyone participant?
Yeah, because next lecture will be of management. So I will talk about those, how the planning and management can be done in the watershed or river basin. Yeah.
Okay, sir, no problem.
Okay. Then we can move to our next session.
Sorry, sir. If you want to sometime, sir, you can take.
Sorry? Hello?
If you want some time, you can.
Yeah, that's what I'm actually asking. 1 minute we can wait so that they can generate some question and I can get some
Yes, sir. Yes, sir.
breathing time.
Yes, sir. Yes.
Okay. I will share my screens. I hope this is visible.
Yes, sir. Yes.
Okay.
Just your presentation mode, if possible, sir.
Yeah, this is a presentation mode only now.
Okay, sir.
It's moving, no?
Sir.
Hello?
Yes, sir. Not visible. Water management, I think. Okay, okay, sir.
It's visible now?
Yes, sir. Yes.
Okay, great. Okay. Thank you for confirmations because I was not, I cannot know whether it's visible or not because I can say everything.
Yes, sir. Yes, sir. No problem, sir. Going on.
Participants must
Okay.
see the things. Okay. Thank you. Okay. Let's go to our second session. That is watershed management and then planning. Sorry, it is the first is the planning and then management. It's not vice versa, but first is the planning and then second is the management. It's more of like a technical as well as some of the concepts are policy or management or some kind of a administration. So it's a combination of 2-3 things that helps in the watershed management or river basin planning and management. In today's okay, and mostly we deal with the some of the aspect of water management here, land as well as water management. So land and both water management, we'll talk about all those things together here. And I will take a one case study which I did for the river basin planning in Karnataka with the help of different all the techniques that is we learned and to estimate many things to come out for the basin planning and then how it can be managed. The water can be managed, how this rainfall can be managed, how the land can be managed, and what are the things to need to change for its sustainability as well as its economic to maintain its economic status as well as the environmental status. So both things are coming parallel together, and environment and economic both are important in today management world. So I will take one example of this basin, that is the one river basin known as Tungabhadra, and I will talk. I will just inform how we did it. What are the layers using the GIS, using remote sensing that we use to determine various water components, various land components, and then how the watersheds are prioritized in the subbasins for maintaining the soil, to reduce the soil sedimentations and to increase the soil moistures, and so many things together. And then we did some climate studies also, how the water can be, how the water has impacted due to the climate change studies. So these are all things have been done for the one basin or one sub-basin, sorry, Tungabhadra. In sub-basin, there were many watersheds, around 15 or 63 watersheds are there, and these watersheds are created separately using this planning. The study location is in Tungabhadra, that is a part of a area of Karnataka, and this is a basin of Krishna. This is a Krishna basin, a big one, where the Maharashtra, Karnataka, Telangana, and Andhra states are involved. And Tungabhadra basin is primarily in the Karnataka. So 90% area of the Tungabhadra sub-basin of Krishna is within the Karnataka, and therefore we choose the Tungabhadra basin to develop a plan, river basin plan, and then for its management of water and land. Here is a quick statistics of how these are the statistics we need to develop for developing any basins, any sub-basin or any watersheds. So you need to develop your data, you need to develop your informations, you need to develop your network to fetch the information for various aspects of the water and land. It is a Krishna basins, and then Tungabhadra and Vedavati is laser points. So this is the Tungabhadra, 39,000 and 14,000 square kilometer, and it is occupying 34% of total area, and 16.24 is of Vedavati, and this is the total number of water availability, 338 TMC. TMC means 1,000 million cubic feet. 1,000 million cubic feet. 338.22 and 33.44 million cubic feet is the allocations. Now Krishna is a interbasin, and therefore the water availability within the basins are fixed. For each state is also fixed, and therefore the state has a limited, or this is a maximum potential water they can be collected or utilized. So the limit is fixed for each state. Okay, and then how many peoples are living in that basins? So around 10.07 million peoples are living, and in this 4.13 million people are living. Now this is a one indicator. If some of the watersheds are scarce, water scarcity is there, or absolute scarcity is there, how we can define the water scarcity watersheds? This is just a simple ratio of how much water is available divided by number of people living in there. So it gives the cubic meter of water per year per person. And as per Falkenmark, if the water availability reduces less than 1,000 cubic meter per year, that watershed or basin is called the scarcity basin. And if that watershed has a less than 500 cubic meter per year per person, then it is absolute scarcity. That means this is a very dangerous situations, and 1,000 is alarming situations, and more than 1,000 to 500 is a surplus basins. So this is how one indication gives a number of your basin is falling into different scarcities. Just a study area, and which includes more than 6 or 7 districts. A one Tungabhadra, big reservoir Tungabhadra, and water flows from, sorry, let me use my pen. And water flows in these directions. So this is a outlet. This is outlet, and this is a watershed, or this is a basin boundary. Okay. So Tungabhadra is very significant for Karnataka because it leaves more than 30% populations geographical area, and more than 23% populations of Karnataka lives in the Tungabhadra. It contributes more than 20% of milk productions, and it contributes more than 37 to the food productions, and then contribution to the economic activity. So out of 122% of the revenue generated in the state is coming from the Tungabhadra. So this way you can develop for all your watershed the significance of that watershed, how it is significant for the people, for the state, for the people that is living, and then its contribution to the economic activity as well as for the people. So giving the importance of this Tungabhadra, the its contribution is very recognizable or significant compared to the other sub-basins. Then we define some vision, that what should be the vision for our basin. Basin vision is secure supply of water. That means security, water security is the first for all the users, like for the domestic, for the agriculture, for industrial, and for environmental. That maximize benefit. So all the all the stakeholders within the basin or within the watershed, they are supplied with the good quality water, like domestic, agriculture, industrial, and environmental, that maximize the benefit. So this is a vision for any watershed or for any basin that can be developed. Now to develop a plan, then you need to have a very good accurate water or very good data, and that should be accurate and reliable. And then we find different data and patterns of various climate, how the climate is behaving, and how the current water use and its impact need to understand the current pattern. Then you can define what are the key issues or key priorities area challenges to be addressed in the watershed plan or river basin plan. So this is a very basic steps to collect the data, to face the data from different departments, from the different sources, and then make the analysis, come out with the its usable format, and come out with the issues or challenges coming from the data. Then what you know is a river basin profile, that is know your basin or know your watershed. We do some baseline situation, baseline assessment. This is the very basic thing in any watershed or in any basin. A baseline assessment or baseline survey to assess the current situation and historical evaluations. Then prioritize issues and principles, indicate what are the key challenges or concern for the planning. Then identify future developments and the trends, provide forecast for scenario development and management pathways. So this is how you define the baseline, what are the data needs, and what is the current situation of groundwater, surface water, water quality, land, watersheds, and then reservoirs, lakes, agriculture. So you need to know the situation of all the land and water managements, all the land and water components within the basins, and then find out the issue from that, and then further develop a plan for the future. Accordingly, we generated many of the data for this. You can see here there are four river, that is Bhadra, Tunga, Tungabhadra, Varda, Vedavati. So 1, 2, 3, 4, 5. So these 5 rivers are actually contributing here, and we can define here catchments here. Here is one catchments. Here is another watersheds. This is another watershed, a big watershed. This one, and this is another watershed. So this is a Vardha, and this is Tunga and Tungabhadra, Bhadra, and this is a big one is a Tungabhadra, and this is a Vedavati. So these 5 watershed we have defined based on its river and then confluence, and then we find out how much is the rainfall in that basin or in the catchments watershed, how much is the annual average flow in the basin, and how much is the area, catchment area or watershed area, how much is the runoff depth, how much is the runoff available at the outlet of that each catchment, how much is the water available each, that is a runoff, and then we find out the how much is the runoff coefficients. Now here you can see here the Tungabhadra, it is 0.6, it is very high, and this Tunga river is here because this is mostly a forest area where Sringeri, Shimoga and all those Western Ghats are Western Ghat forest plantations and other things are available, and therefore this Tunga river is having a much of the runoff from the rainfall and so on. And Vedavati is very less than even 0.1 because it is a completely dry, rainfall is very less, and the average flow is also very less. So likewise, you can then define how the watersheds are behaving. This is just one example using the help of rainfall and runoff, and then calculating the how much is the runoff coefficient in that particularly watersheds. Then you need to find how many water bodies are there and what is its storage capacity. So we found there are 7 major storage are there, and capacity is around 200 TMC cubic meters. Then we found out how many gauging stations are there. These gauging stations are placed in each of the river to measure the runoff in the streams, and these are maintained and managed by the Central Water Commission where they measure the flow, that is the outflow from the generated from the each catchment. You can see here the annual flow in TMC and the record year for which year it has been combined. Then we try to fit a one water balance. How much is the water available for each basins using the major and medium irrigation projects. So major irrigation 300 TMC is available. For minor irrigation 64 TMC is available. So total water available is 371 TMC. So do we have enough storage to accommodate allocations? 70% dependability, that is the criteria from the Krishna Water Dispute Tribunal. This is a Krishna Water Dispute Tribunal because it's an interstate river. So it is governed, the water availability and allocation is driven by the Krishna Water Dispute Tribunal. And they have defined a 488 TMC of water. However, the actual uses is 371. So there is a more water is available to use. So do we have enough storage to accommodate the allocation? That is the basic question that appears. Then what are the allocation for the different users, water users? First is agriculture, then drinking and industries. Agriculture, drinking and industries. And you can see here the 94% of the water in the basin goes to the agriculture, and less than 2% of water goes for the drinking, and more than 3% or less than 4% of the total water is used for the industries. So industries also using, and their trend is also increasing. So industries are asking more water compared to the domestic and drinking, and that should come from the agriculture. So that share has to come from the agriculture water use. And then water allocation to the industry is more compared to the domestic in supply in last 10 years. Now the trend that we obtain is the industry is using more water compared to the domestic. That means the competition from the industries is more compared to the domestic water supply. So this is how you generate a statistics and then find out the concern for the future direction. Then we find out how much is the groundwater availability and its use. And we found around these hectare-meter, that is in hectare-meter, net availability, and this is the existing water used for irrigations, and this is for the industries. So in this case also you can see here the agriculture is using more groundwater compared to the industries and domestic. Now trend in irrigation using groundwater. You can see here the trend from 2001 to 2014 and 15. The trend is increasing. Earlier it was only less than 500 hectare-meter. Now it has gone to 800 hectare-meter within a span of 14 or 15 years. So total gross irrigated area increased by 75% with the help of groundwater. So groundwater utilizations for the agriculture is increasing day by day, and that is gradual increasing. You can see here the irrigation through different source. Then what are the different source? Net irrigation tube wells, it's comes in around 45%, and then this is 5% left irrigations, and then canal irrigations, and then this is the irrigated tanks, and then further. You can see here in this the irrigated land uses 45% of water. So percentage of net irrigated area by groundwater is 45% vis-a-vis 36% by the canal. So surface water is less utilized compared to the groundwater. This is one trend, how the gross irrigated area by canal is remains same, but well it is increasing. This is a well. So from 2000 to 2014-15, the groundwater well irrigation is increasing. That means they are taking more groundwater for the. Then we found out what is the exploitation of the watersheds from the groundwater perspective. There were total number of 61 watersheds of more of 700 or 600 hectare area, and then 33 were in the Tungabhadra and 28 were in the Vedavati. So we can see here the overexploited mostly. These are the safe. Sorry. Then criticals, and then semi-critical, then critical, and overexploited. These are the categories of different watersheds where the groundwater was exploited more. Then we found out how is the demography or the population is behaving, and then we saw that as per 2021 census, the total population 14.1 million, and then range 191 in rural areas and 260 in urban areas. And the growth rate of urban population is 31%, which is 4 times higher than the rural population growth. So we found that the urban population growth is more than 4 times rural population. So urbans are developing more compared to the rurals, and therefore the urban water demands is increasing, will increase in the future also. Then socio-economic status of the basin. This is how total literacy ratio 88%, and food production is 32%. and total 30% geographical state area. Now, one of the important things that I would like to mention here is the agriculture, forest logging, and fishing. These are the sector-wise contribution to the GDP. Now, if you see here, 2001, 28.2, and 2014 is 9.6. So agriculture contribution to the GDP, state GDP is reducing minus 59.9%. However, fishing, it is increasing. It was only 0.5 and 0.6. And therefore, they are thinking that agriculture is contributing and the growth is negative compared to the fishing and other livestock and other things. They are giving more priority for the fishings to generate the income for the farmer as well as the income for the state. This is just which district is contributing more in what sector. So Bellary, which is contributing 4.3% to the state GDP, is through industries. So they are, the Bellaris are the most, Bellary steel plant or this GSW industry, steel industries are there. They are using the more water and contributing 4.3. So this is particularly industrial belt. And this is Gadak is especially a service industries and rest of the agriculture and allied sector. This is how you can demarcate your areas for different sectors and what are the contribution to the different sectors. Then we find out the what is the climate is increasing or decreasing or what are the changes. The 10 changes we see here is the average temperature is increasing in the basin. Average temperature from 1951 to 1986 and so on. The monthly temperature is also from the, if you see here, the average monthly temperature 50, the red dot is 51 to 19 and 91 to 2004, the monthly temperature is increasing in the basin. So once the temperature increases, the evaporation and evapotranspiration increases and the water demands increases for the agriculture also. This is the one pattern that we received while we obtained after analyzing the data. Then rainfall patterns. Then we saw the rainfall, how it is behaving in different basins like Bandra, Tunga, Tungabhadra, Varda, and Vedavati rivers. So these are some of the catchments, and these catchments, how the rainfall is behaving. So particularly the rainfall is remains same. It's not changing much. However, then we saw the monthly rainfall also. It is quite high in Tunga because it is upstreams. So it receives more rain compared to the Vedavati and Tungabhadra river. Then we saw the rainfall change from 1951 to 1990 and 91 to 2007. So rainfall is also increasing. You can see here the blue line for the month of June, July, and August. It is increasing from the base of 1950 to 1990 and to 2009 to 2017. So rainfall is also increasing. Potential evapotranspirations. This is a evapotranspiration. This is a potential. This is a maximum evapotranspiration that can occur in that basin or sub-basin. Here it is almost same. Now you can see here the rainfall is much higher in the Tunga. However, the potential evapotranspiration remains same. That means the vegetation is occupying, vegetation is contributing more in the evapotranspiration for Tunga also. Then topography, we define the how do the slopes. Mostly these are the flat lands. This is a flat land. This is quite undulating, and this is very slopey lands. These were the some of the slopey lands. Western Ghats having average mean sea level of 1,200 meter, and the rainfall is around 2,300. The rainfall intensity or rainfall amount decreases from this way. Then land use, land cover. Then we found the forest is increasing by 0.02% since 1989. Because of many social forestry and many forest department programs, the forest cover has increased. And you can see here the contribution from the forest is around 56, 60, something around 20, at 18 to 20%. 18 to 20% is the forest cover in this case, and agriculture is more than 60%, and then plantations, and then built up, that is urban areas, grassland, and then water, so on. So this how you land cover and land use, and then various categories, and then is percentage of different for the land use. Then agroclimatic zones, these how many agroclimatic zones are there? There were 6 agroclimatic zones. Then land use land cover, this is the pattern of land use land cover. You can see the forest is mostly on the upstream side, cover is there, and for the lower side most of the time is agriculture lands, flat terrains. You can see here this is agriculture lands, this area, and the forest is very less in these areas because of the dense forest. Then you can see here the land use change pattern from 1989 to 2014. Then we saw the land available for the cultivation, not available for cultivation, is increasing. That means the agriculture land is converted into the non-agriculture purposes, and this is mostly due to urbanizations for the various road projects or various industrial units. The agriculture land get converted into the non-agriculture land, and therefore we find that the agriculture land, availability of agriculture land is reducing in this area. This is the number of various crops that's grown in that area, and then how is contributed cropped area as well as irrigated area. Then this is a cropping pattern. Then clay soil is mostly clay soil in the entire basins, bit of loamy soil, clay and loamy. So this is a mix of clay and loamy soil. There were large command areas from the major medium irrigation projects. You can see here these were the command areas. And then from last 23 years, the Karnataka is implementing many watershed programs. First is a National Watershed Development Program for rain-fed areas, NWDPRA, then River Valley projects, then Drought-Prone Area Development Program, then Integrated Westland Development Program, then Desert Development Program, Western Ghat Development Program, Social Component Plan, then Tribal Sub-Plan, Karnataka Watershed Development Project, DANIDA, KWDP, and reclamations of soil, and World Bank Assistant Sujla projects. So from last 23 years, number of programs are being run and implemented in those basin and then these watersheds. And the result is that their watershed areas are being created for the soil as well as water conservations. And the most importantly, notably, the River Valley project, where the sedimentations has been reduced reduced to the Tungabhadra sub-basin, because Tungabhadra sub-basin is the most silted tank in the India, and therefore this River Valley project was implemented to reduce or to stop the soil erosion and sedimentation in the Tungabhadra. Then water dependent systems. The water also need to the various national parks, religious places, and some sanctuaries, and those are also need to think and give allocation for those. We found that there were no water sports and water tourism, and therefore the water allocation to those areas were not available. Then we found some water quality, drought and floodings in Tungabhadra also. There was a water quality issue in those areas because of the many industrial unit, and from the agriculture point of view also, the most of the agriculture pollution is from the non-point source from the agriculture, where the most of these areas use the fertilizer for their irrigated rice, and then the fertilizer used to drain to the stream, and that accumulate the that reduces the water quality and become unfit for the drinking to the cattle as well as human. These are the water qualities stations. These are the how the water quality is reducing. Here water quality is reducing. Here water quality is reducing from 2004 to 2013. It's going to C. There are various categories that A, B, C, D. D is a total unfit. A is fit. B is suitable for. B is suitable, and C is fair. Something like that. There is a water quality manual where you can find out this A, B, C, D parameter. And this is the BOD, biochemical oxygen demand in the water levels. So this water has a capacity to carry the oxygens for the aquatic animals like fish or crocodiles, and many few plants and animals lives in the water. They require the oxygen, and therefore the water oxygen in the water is important for the aquatic animal, and they measure as a BOD, biochemical oxygen demand of the water. This is a river health is deteriorating. In this case, you can see here, here the water is now being less and the more encroachment in those areas is happening. Groundwater quality is reducing in many because of the large amount of water is being extracted from the groundwater. This is particularly from the very lower strata where chlorine is mixed with the pumping of the groundwater and become unfit for the drinking also and for agriculture also. So this agriculture, then you can have electric conductivities more than 2000. Sometimes it is lower than 2000 in those areas. So that is really unfit for the agriculture also or for irrigations. If it is electric conductivity is more than 2000 micrometer per centimeter, then centimeter square, then it means unfit for the agriculture irrigation also. Then groundwater quality for the chloride, if it is more than 1000 milligram per liter, then it is unfit. Then fluoride, the nitrates, and so on. And then we found out the drought, how the droughts are also behave from the last 10-15 years. And we found that more than 51 talukas are experiencing drought in 41 talukas, and these are the severity index. So red is the very severe. This is almost every year there is a drought in these areas. In these areas, there is every year drought in these areas. And these are the flooding. These are the most susceptible to the flood also. See, you can see here, this area is drought as well as flood. So both simultaneously. So this is how you can compare that the area which are prone to the flood and which are prone to the more drought, looking into the various trend of flood and droughts. Then we found how many how many departments are working in that sector, water sector, and directly involved or indirectly involved in maintaining, using, or managing the water. We found these many stakeholder, national level, Government of India, then Ministry of Water Resource and River Development, and now it's Jal Shakti, then Central Water Commission, Central Groundwater Board, Central Groundwater Authority, Central Groundwater Pollution Control, Water Quality Control, Ministry of Environment, Forest, Ministry of Agriculture, Cooperation and Farmers, then River Board, constitute Ministry of Water Resource, that is Jal Shakti, Krishna and Godavari River Management Board, and Tungabhadra Board. These are the some of management bodies are the departments directly involved into the management of waters, and these are the state water department and institutions directly involved into the management, maintenance, and the using of water. That is Water Resource Authority, then State Planning Board, Water Resource Department, Karnataka Niravari Nigam Limited, Command Area Development Authority, Minor Irrigations, Groundwater, Karnataka State Natural Disaster Management Centers, Department of Ecology, Department of Agriculture, Department of Horticulture, Watershed Development Programs, Karnataka Forest Department, Karnataka Urban Water Supply, and Karnataka Rural Water Supply, and Panchayat Raj Institutes, and Department of Industries and Commerce, and Karnataka Power Corporation. So these number of boards are involved, number of departments, and these are the some of the direct involvement of those institutes and departments in the water. And these are wholly responsible for are acting or maintaining the water resource. And therefore their participation is also important. And we hold the various consultation with those departments, about various aspects that we develop. And then we found that there are some challenges after looking into the data, different things. The climate can affect the water flow. Water security is low in the basin. The water quality are monitoring and it's degrading. It's a less coordination of different sectors. The inflow to the reservoirs are reducing. Groundwater is depleting. Sedimentations in the rivers and reservoirs are serious, and river health is in poor, and frequent occurrence of drought, and the basin is an income loss to the agriculture. These are the major finding of our basin. So these concerns are the after reviewing the situations, then we found these are the main concern that is to be dealt with the plan. Then we found out what are the assets in the basin. So major rivers, major reservoirs, irrigation schemes, and watersheds are the asset for the basin. Then we found what are the factors impacting the water availability. So there are many factors that impact. Was the information, there is a less of data. Watershed management is poor, infrastructure is poor, institutions are poor, river and environmental qualities are poor. So that is leading to the insecure water availability or various users. And after reviewing this, then we develop a plan that we plan for the key result areas. And these key result areas are: we secure supply of water to rivers, then groundwater, and then water quality, and then governance or management of K89 basin. And then we found that these basins should be protected. These watersheds should be protected to maintain the flow in the downstream areas. And then we found the groundwater. We found that these watersheds, Hirella watersheds, and these watersheds are contributing more to the soil erosion to the reservoir. So these to be treated again to maintain or to reduce the soil erosion. And then we define some actions. What are the operations, activities for department-wise actions? Then these watersheds need to be develop a security plans, monitor the groundwater levels, and implement water security plans, and then vulnerability watersheds due to soil erosions. This is protect the water qualities for at two places. This is one, and two places we found the water quality is to be maintained. And then we recommended a river basin management or the watershed management in different watersheds and for the basin also. So we have a watershed management as well as river basin management on top of it. And then we suggest a various executive bodies, committees, and then standing committees to administer this basin plan and then watershed plans, and then define those things. These are some of the key result areas, and their budget also suggested budgets and who will implement what kind of things. And we conducted some workshop with those higher authorities for implementations, where the chief engineer and super engineers were involved. Then we involved some water quality peoples from the State Pollution Control Board. And that's all. So this is how we develop a plan and then given for implementations to the various department in the basins. This is all from my side. I'll stop my presentations. Okay. So if you want to know more about any of the two lectures or previously one lectures about remote sensing and GIS, would like to know about more, or would like to know the things, please, you can unmute and speak.
Thank you, sir, for your valuable guidance to the participants.
Yes, sir.
Any participant want to ask any question? They can ask by unmuting themselves.
Yeah, or any information or any kind of inquiry, something like that. Okay.
Hello, sir. Excuse me, sir.
Uh-huh.
Sir, in this Tungabhadra case study, you have provided too much numerical data, sir.
Sorry?
In this Tungabhadra case study, you have given too much numerical data to us.
Yes.
But we don't know. We don't know case study will come in the exam point of view.
Okay.
Hello, sir.
Yeah.
In exam point of view, they want to ask case study, I think.
No.
We need general view, general content related to watershed management. That's what I'm asking.
Yeah. They will ask only general watershed management, but watershed management is deal with the most of the water management and land management. What soil conservation measures and water conservation measures you are going to do. So mostly the soil conservation measures like contour band, trace band, terrace gardening, and all check dams, gully plug, cabin structures. Those are the water conservations. And the land managements, how the land will go for the agricultural land and pasture land and some agriculture or storage for the water or recharging the groundwater. Those kind of things are required for the watershed management. Now you can see here the watershed also, some of the watersheds are depleting and the groundwater is also reducing. Now why the groundwater is reducing? Because there is a much of the pumping of water is going on due to the free electricity or due to the indiscriminate use of groundwater and due to the high intensity water crops like sugar cane or like rice. So they take more water and then productivity of that water is also less compared to the other crops. So this is how we can make a combination that we should have a less water consuming crop versus high consuming water crop and see their water productivity in terms of kg cubic meter of water. That means amount of biomass or amount of grain that produced from the 1 kg of 1 cubic meter of water. So those kind of analysis that can be done for any watersheds and other things. So see, the basic principles remain the same for anything, whether you take the watersheds or you take the now you see there should be a watershed development committee for the watersheds, and there should be some secretary, and there should be some president, and then some members of the watershed committees, which have their own accounts in the bank, and they do all kind of transactions for their needs. Once it is approved in the Gram Sabha and in the Watershed Development Committee, then it goes to the construction and then finally tendering to the local areas. So this is, and then they go for the either check dam, percolation, recharging shaft, or recharging groundwater. So and they, depending on their situation and depending on the local needs, they go for the water conservation and soil water conservations.
Oh, okay, sir. Thank you very much. Sir, what are the areas may chance to ask the questions in exam point of view? That's what I'm asking.
Okay, yeah. From the exam point of view, this is more of a kind of a project, but this from the exam point of view, you can go for the detail. What are the different watershed programs that has been run in Maharashtra or in the Department of Watersheds or Department of Agriculture. Now, Department of Watershed is under Department of Agriculture. So, what are the different programs that is being that is run by the suppose somebody asks the River Valley project. What is that River Valley projects? So you can learn about what is the River Valley projects in that. So now there is one more program, that is a Pradhan Mantri Krishi Sinchai Yojana.
Yes, sir.
That is purely for the agriculture, where the micro irrigation scheme is planned micro irrigation schemes are planned for the many areas to increase the water productivity. The water productivity means a kg of biomass from cubic meter of water. So those things are available. I have given you some few key things. You can explore those more. Okay, thank you.
Yes, sir. Thank you, sir.
Any other want to ask something?
Yesterday session also you can ask from the yesterday session also. Okay.
Nana Sahib, if there is no any query, we can conclude the session.
So we are very much appreciate and thankful to you, sir, on behalf of Department of Agriculture Extension and Communication Department, PGI MPKV Rahuri. You have explained all topics regarding to the watershed management in a very excellent manner. Even so, it is a very technical subject. In the previous lecture, you have also very nicely explained GPS, GIS, then remote sensing. In that lecture, you have explained how to read the topo map, delineation of watersheds, shapes of watersheds, size ranges of different hydrologic units, then their morphological characteristics, components of watershed management, different measures of land management. In another lecture, you have also explained river basin planning and profiling, groundwater availability and use, trained in use irrigation of groundwater, then irrigation through different sources, watershed in basins, demography, and all that thing. So thank you so much, sir, once again for giving your valuable time and guidance. Thank you so much, sir.
Okay, thank you very much. Okay, shall I close my?
Yes, sir. Yeah,
No problem.
you can leave.
Okay, thank you.
Okay. Thank you, sir. Thank you very much.